Welcome back. In the last lecture, we developed an intuitive understanding of simple linear regression. In this lecture, we'll formalize this intuition. Let's get started. In order to formalize our intuition, we need to first take care of some definitions. In machine learning, parameters refer to the values that we desire to optimize. And in the case of simple linear regression, this is theta 0 and theta 1. Training refers to the models finding the optimal parameters for a given task. And sometimes training is also referred to as learning, but they both mean the exact same thing. The testing of a model refers to using data outside of data used for training to see how good the model is doing. We will learn about each of these terms in greater detail in this and later lectures. Now let's go on and formalize intuition behind simple linear regression. Essentially, we have two paired data sets, X and Y, and we aim to predict Y using X. In machine learning, we let X to be a matrix of values, and we let Y to be a vector of values. In other words, we have various paired sets of X and Y, and we aim to use that to train our model. And as stated earlier, we want to determine a function that models how bad the model is doing. And in machine learning, this function is often called a cost, or the loss function. And we call this function j of theta, taking in parameters theta 0 and theta 1. And in order to minimize this function, we need some algorithm that optimizes the function. And in this case, we want to optimize the cost function. And now that we have broken down this problem in three formal steps, that is collecting various X and Y pairs used for training, creating a cost function, and then using some optimization algorithm to minimize this cost function. Now we can dive into each of these characteristics in greater detail. The first step in linear regression is data collection. And we want to collect as much data as we can. And up to a certain point, the more the data, the better the model. And as stated earlier, we want to collect paired sets of data. An example of 5 paired sets of engine size, the cost data is shown here. And we want to use this data to train the model. And now let's go on to step 2. Recall that a cost function is a function that measures how bad the algorithm is doing. And there are two main types of cost functions for regression, both relying on the idea of using distance between the predicted line and the data points to measure how bad the model is doing. The mean absolute error cost function calculates the absolute distance between the predicted line and the data points, and then averages it for all data points. And mathematically, this is written as such. On the other hand, the mean square error cost function is the same as the mean absolute error cost function, except it squares the distance instead of taking the absolute value of it. Mathematically, this is shown as such. And by the way, in the mean square error cost function, 1/2 is multiplied by the average error, and that is because this just helps the numbers work out a bit nicer. And in practice, the mean square error cost function is usually used more than the mean absolute error cost function due to 2 reasons. Firstly, it penalizes values that have a very high distance from the predicted line more severely than the mean absolute error. Furthermore, gradient descent, which is an optimization algorithm that minimizes the cost function to find the most optimal values, works better with the mean square error cost function than the mean absolute error function. And that's it for lecture 3. In the next lecture, we'll learn about various different optimization algorithms, such as gradient descent. See you in the next lecture.